In this video, I introduce learning to drive using inverse reinforcement learning and DeepQ network. Reinforcement learning formulates the interactions between the agent and his environment as a Markov decision process. That is, the table includes state, action, state transition probability, discount factor, and the real-world function R. And then we use three functions to describe the Markov decision process. One is policy, maps from state to action. And another one is expected state value function to describe the property of this state. And action value function, SQ, is a Q function, describe state and action. So suppose we have expert demonstrations follow the expert policy. Inverse reinforcement learning is used to find the real-world function for the optimal policy from this expert demonstration. And then once we have the real-world function, we can use reinforcement learning to find the optimal policy for agent. The purpose is we make this difference as a minimum. One is the state value function and the learned policy, and this is the state value function and the export policy. That means we try to find a policy which close to the export policy. To find the real-world function, first we assume real-world function R is linear. Linear means we can express the real-world as the parameter R that is to be determined. And the feature vectors is unknown. And this basis function. So once we have this, you assume this real world is a linear function, then we can substitute this real world into the expected state value function and move this W out of the sum and the expectation. Since this term is no relation with the W, we defined as a feature expectation, denoted as mu. So the reinforcement learning method, we try first use the expert demonstration and the inverse reinforcement learning to find the optimal policy. So to find the real-world function. In this way, without manually designed real-world function, we can use that real-world function in the reinforcement learning to find the optimal policy for agent. The goal is, we find the policy we find is close to the export policy, so that the state value function and the learned policy is closer to the export policy. And then let's see how can we use the projection method for inverse reinforcement learning to find the parameters W. That means we need to solve this maximum minimum problem with a constraint. Here, this T is a margin between the state value function and the export policy. This one is the state value function and the learned policy. Here, just regularization makes this W is smaller than 1. In the inner term, we need to find a policy, make the mu value has a minimum difference from the export value. That means we need to find a policy to close to the export policy. And then we try to find the W for this optimal policy, make the real world is a maximum. That's the goal of the reinforcement learning. And to do so, we use a projection method. Projection method means we have a previous mu, we have a current mu, and we have export mu. And then now we've tried to project this export mu to into this line and find the mu which is closer to the export mu. Of course, it does mean this linear between this point and this point. We just try to find one policy which has a mu which is close to the export mu. Here is right now the projection method is used for the inverse reinforcement learning, just to find this W. Once we have this W, from W we can find the reward R. And then now we use the R in the reinforcement learning, find the next pi policy. And then now we use the pi in this formulation calculator mu. So once we have the new mu, and then now we have two mu's, and we have export mu, and from this interpolation, we can find this mu. So from this mu and the export mu, we can find the new parameter W. Once this T is smaller than criterion, then now we stop the iteration. That's the idea for the reinforcement learning. How can we use the projection method to find the W? And then from W calculate the reward used in the reinforcement learning to find the next policy. Once we have a reward from inverse reinforcement learning, then we can use the deep Q network to find the optimal policy. Here, if we use the deep Q network, of course we need to use the experience replay to get a stable result. And then we also need a target network. We don't need a train, we just use a target network to generate a target here. And this target plus, this reward from inverse reinforcement learning, and then we get a target to train this Q network. The Q network has the input. This input is the feature vectors, and output is the Q value over all the possible actions. That means, from the Q network, we can find which action is optimal policy. So once we have this optimal policy, that means we have a policy, we can use a policy, give this policy back to give the policy to the reinforcement learning to find the mu value. And then we update it to find the W, and from W from the R, we give this R to the Q network. Q network generates a policy and give policy to the inverse reinforcement learning. In this this way, we can finally find the optimal policy without manually design the reward function. For more details, please check with this reference. Thank you. Bye.